So the next speaker is Professor Yang Li from MIT, and he is a winner of Frontiers of Science Award. And his title is Exotic Calabi Yau Metric and Holomorphic Fibration. So let's welcome.
Thank you. It's my great pleasure to speak at this conference. It's a wonderful conference so far. And so today I'm going to talk about Calabi Yau metrics, and it's supposed to be quite introductory. So sorry for the experts. So Calabi Yau manifolds are Taylor manifolds with a nowhere vanishing holomorphic volume form. So this, so let me just first say that the simplest example of this is just the Euclidean example. So what kind of data does this involve? Well, so this is a Taylor manifold. So in particular, it's a complex manifold. So it has a complex structure. And on top of that, you have two pieces of equivalent information. So you could either think of this as a symplectic form omega, which is compatible with J, or you could think in terms of the metric. So this is a Riemannian metric, which is related to this omega by saying that omega is T of J dot. So equivalently, you could specify either the symplectic form, also known as the Taylor form, or you could specify a Riemannian metric. Now, Calabi Yau metrics are by definition metrics satisfying the following equation. So here, capital omega is something called a holomorphic volume form. Maybe the simplest example of this is if you're on Cn, then this is something which looks like dz1 wedged onto dzn. This is a degree n form inside a complex n-dimensional thing. So just for people who are not that used to complex world, so the complex dimension n is real dimension 2n. Okay. So this is not quite a volume form, but you can produce a volume form by taking this thing and its complex conjugate, omega bar, and you wedge them together. That would give you essentially a volume form. And the Calabi Yau condition is just saying this volume form is essentially the volume form induced by the Taylor metric. So this one would be the Riemannian volume up to a constant. Now, this equation is also called the complex Monge-Ampère equation for later use. So the reason people care about this, one of the main motivation of this is that if you have a metric like this, then the associated Riemannian metric is Ricci flat. So the Einstein Ricci curvature is 0. So the vacuum Einstein equation is satisfied. So that's one of the historical reasons people first care about this. In fact, the whole field of Kähler geometry, I think when Kähler first introduced his metrics, he was thinking about trying to find Ricci, trying to solve the Einstein equation. And what he noticed was that if this omega is defined by the complex Hessian of some potential function, so nowadays we call this kind of thing Kähler potential. So the point of this is that the metric is a tensor, while phi is just a scalar value function. So what Kähler noticed is that if your metric comes from a single value potential, scalar potential, which is much easier than a tensor, then the Ricci tensor has a much easier expression, and it reduces to a much simpler equation. So yes, the foundational theorem in this field is, of course, Yau's theorem on compact Calabi Yau manifolds. So that theorem says, okay, so first of all, for metrics, you can associate, so omega is a closed form, so you can take its cohomology class. This thing is known as the Kähler class. So Yau's theorem says, suppose you give me a Kähler class on a compact Kähler manifold, and you know that this manifold has a nowhere vanishing holomorphic volume form. So far, these things can be checked very algebra geometrically. Then there exists a unique Calabi Yau matrix, meaning a solution of this equation inside this given Kähler class. So this is a very satisfactory result about existence. Now, there are certain questions that this doesn't quite answer, such as, what this metric actually looks like. So the proof is by some a priori estimates, and it doesn't quite tell you what the solutions explicitly look like. And neither does it tell you, what would happen to the solution if either your Kähler class or your complex structure becomes degenerate in some way. So these are the kind of major questions in this field. So almost all the compact examples are not explicit. So the only completely explicit ones known to me is just the abelian varieties. So things like elliptic curves. So other than that, everything else is obtained by some kind of gluing construction, or the ones that you do have descriptions. So they would be not completely explicit, but maybe sometimes explicit up to perturbations. Now, you could also ask about what happens to the non-compact world. So in fact, most of this talk will be about that. It turns out to be very much intertwined with what happens in the compact case. So in a non-compact world, there are many examples which are completely explicit. So sometimes there's a kind of contrast. So the compact case, you have a very satisfactory existence and uniqueness result given by Yau. In a non-compact world, there's nothing that in that generality. So there are many constructions, many of which are explicit, but there's no kind of completely general structural kind of classification in for generality. There are many cases which are well understood, but not all the cases. Now, one of the main messages of today is that the non-compact examples should be viewed as the building blocks of the compact examples. So when the compact examples are close to some degenerate limits. So what do I mean by degenerate limits? Well, so Yau's result tells you that the Calabi Yau metric essentially depends on two pieces of data. One is the Kähler class, the other is the complex structure. Now, one of the two things may happen. Either the Kähler class may tend towards the boundary of the Kähler cone. We will see some examples of that later. Or the complex structure might become degenerate. So an example of complex structure becoming degenerate is if you have an elliptic curve, it might converge, to something like this. Eventually, it might become S1. So limits of Calabi Yau metrics are not necessarily Calabi Yau. It might not even live on a complex manifold. Now, let me give you some explicit examples. In fact, I think I will only tell you two explicit examples other than the Euclidean one. So the Euclidean one is the simplest one. So this is almost like the next simplest you can get. It's called Iguchi-Hansen matrix. There are many descriptions. So this is one that I will use later. So these metrics live on this explicit affine quadric. So this is a hypersurface inside C3. It's a complex two-dimensional surface. It's defined by a quadric equation here. Y is just a parameter. This is an equation in the three complex variables. And one way to specify a Kähler metric is just by writing down a Kähler potential. So the way metric is related to the Kähler potential is just you take the complex Hessian. So this is a completely explicit construction. For this example, the Kähler potential is written very, very explicitly. So you have this function, which is the sum of modulus squared, and you take some square root like this. It gives you a metric. It turns out to be Calabi Yau. Now, the asymptotic behavior of this metric is C2 over Z2. Now, where does this C2 over Z2 come from? Well, first of all, when you set y equal to 0, this is Z1 squared plus Z2 squared plus Z3 squared equal to 0. This is obtained after a simple change of variables. You can write this as Z1, Z2 is equal to Z3 squared. This, it's not too hard to see. This is the same thing as C2 over Z2. So in a special case where y is equal to 0, this reduces to C2 over Z2, and the metric there is just the orbifold Euclidean metric. For general Y, well, when you are going to infinity, the fact that you turn on this finite value of Y doesn't make much difference. So what happens is that the asymptotic behavior at infinity on this guy is just modeled by C2 over Z2. Now, one particular consequence is if you look at the geodesic balls of radius r, the volume of that geodesic ball grows like r to the fourth power, where 4 comes from the fact that you are on a complex two-dimensional thing, so the real dimension is 4. So the volume of the geodesic ball grows like r to the real dimension. This is known as the maximal volume growth case. The reason it's called maximal is because there's a general fact in Riemannian geometry. So suppose your Ricci curvature is equal to 0, solves the Einstein equation, then the volume of the geodesic ball divided by the Euclidean volume of the corresponding geodesic ball with the same radius, that quantity is always bounded above by 1. So this is the maximal order of growth that you can possibly have. It's known as maximal volume growth. This metric also has some obvious symmetries, so it's clearly symmetric under SO3, and it has some generalizations to high dimensional quadrics. These ones are known as stencil metrics. So this is what I would say is the prototypical behavior of what you might have when your maximal volume growth. So almost every maximal volume growth example is in some sense a generalization of this example. Now here is an example which is not maximal volume growth. It's known as the Taub-NUT metric. This is the metric is explicitly written like this. So here the x1, x2, x3 are so-called Gibbons-Hawking coordinates. This theta is a S1 connection. So V is a potential function, sometimes known as a Gibbons-Hawking potential. It's basically a solution of the, let's say, Laplace equation with prescribed singularity. So basically, the metric is very explicit, and it's not totally obvious, but not too hard to see either, that when A is equal to 0, this metric is the same thing as the flat C2, where the x1, x2, x3 comes from the fact that this thing is a hyperkähler metric, meaning it's a complex manifold with respect to 3 different complex structures, and you have 3 corresponding symplectic forms, and the x1, x2, x3 are the 3 moment maps for that. So x1, x2, x3 are not complex coordinates, they are real coordinates. Now when A is bigger than 0, the asymptotic geometry of this thing, it's an S1 bundle over R3 outside a compact set. So what happens is this. So you have 3 real directions along x1, x2, and x3. The whole thing is an S1 bundle over this thing. So there are 3 directions where you can grow, and there's an S1 bundle where the S1 fibers asymptotically near infinity, the length of those fibers tend to a constant. And that constant is kind of inversely related to A in some way. So when A is bigger than 0, then those S1s have finite length as you tend to infinity. So there's one direction where the volume growth is kind of constant, and there are 3 directions which give rise to volume growth. So in total, the volume of the geodesic ball grows like r cubed instead of r to the 4th power.
The previous one is AL.
This one is ALF.
AL.
Yeah. It's maybe the simplest example of ALF. So a fun fact will be important later. This one is biholomorphic to C2. It's not an obvious fact, but it was first observed by Lebrun that in fact the Taub-NUT metric is the same complex manifold with the same holomorphic volume form as the standard C2. Now this is an important lesson because it tells you that on C2, there's more than one Calabi Yau metric. Now, this is something which doesn't quite happen in compact examples. In compact cases, the complex structure plus the Kähler class completely determine the metric. In non-compact case, well, C2 doesn't really have any room for kind of changing the Kähler class. I mean, there's only one cohomology class, which is 0. So on the other hand, C2 does have, non-trivial Calabi Yau metrics. So here is the word in the title, exotic Calabi Yau metric. It just means something on Cn, which is not the flat Euclidean metric. Okay, so this Taub-NUT metric is already an exotic metric in this sense. However, it is not goes out Q. Now, the way you should think about this is that Iguchi-Hansen is the prototype of maximal volume growth examples. And when you try to study compact examples, these things naturally arise in situations with non-collapsing degenerations. So for instance, it appears in certain gluing constructions on Kuma surfaces. Now, on the other hand, the Taub-NUT metric is the prototype of non-maximal volume growth examples, and it models collapsing behavior. So a typical example of collapsing is elliptic curves undergoing this type of degeneration. The kind of hallmark feature of collapsing is that in a limit, something drops dimension. So this is similar to what happens in Taub-NUT. So in Taub-NUT, if you try to scale down the metric and take the limit, what you get is R3, because as you scale down the S1, the S1 has bounded diameter. So as you scale down, this diameter becomes 0. So in the limit, you get flat R3 in the limit. So that's the asymptotic cone at infinity for Taub-NUT. So Taub-NUT is related to collapsing behavior, something drops dimension, whereas Iguchi-Hansen is related to non-collapsing behavior. So where the limits have the same dimension. Now, let me switch to kind of more general frameworks. It was first, I guess, pointed out by Yau in his ICM address or something, that there is an analytic perspective to finding non-compact examples. Now, what makes this proposal popular to many people is the work of Tian Yao in the 90s. And later, Hai refined this proposal, developed a package out of it. So this whole thing is supposed to try to find non-compact Calabi Yau metrics. And one of the sample results given by Tian Yao in the 90s is that on the complement of a smooth anti-canonical divisor inside a Fano manifold, you can find a complete non-compact Calabi Yau metric. Now, let me say a few things about what gets into this sort of constructions from an analyst's perspective. The basic strategy is to construct a Kähler metric on this non-compact manifold where you want to find a Calabi Yau metric, which is asymptotically Calabi Yau. So what does that mean? So Calabi Yau means you satisfy this equation. Let's not worry about the constant. So you could try to first construct a Kähler metric, omega, and this quotient would be a measurement of the error, right? So what you want to have is that this thing is 1 plus something small. So where the small means something which decays at infinity. Now, what the strategy means is that if you can first write down some omega, whatever the source of omega is, so suppose you can write down something where this small thing decays sufficiently fast near infinity. Okay, then there are some general machinery which allows you to perturb this ansatz that you write down into an actual Calabi Yau metric. So this is the philosophy of this analytic approach. So morally, what happens inside a compact region? So in a compact region, this doesn't need to be small. So the small thing is only small asymptotically, and it needs to decay sufficiently fast. But what happens inside the compact region is that Yau is basically Yau's solution of the Calabi conjecture. And what happens near infinity is, morally speaking, perturbation theory. It's not exactly that, but morally. So more technically speaking, that's just for people who are interested, what one does is to solve a family of viscosity equations with slightly negative Ricci curvature. So that's analytically more well-behaved compared to zero Ricci curvature, which is what you want to get in the end. And then you try to prove some uniform estimates on the Kähler potential and the higher derivatives of the Kähler potential. And in the end, you want to take a limit. So that is roughly what goes into this Jian-Yau Hayo-Heim package. Now, the bound on the Kähler potential uses some weighted Sobolev inequalities and weighted Moser iterations. Now, let me comment on one thing, slightly technical, which is that you want this error to decay, to be not just small, but actually decay sufficiently fast. And what that sufficiently fast means is that it's faster than quadratic. So, you have some point in the interior. Let's say you have some distance to the origin, and sufficiently fast means that it is at least this fast. So this is more than quadratic. Now, the word quadratic has a certain meaning here, because if you think about the linearized equation of the complex Monge equation, what you get is this Poisson equation. So for the Poisson equation, if you want to produce a bounded potential, meaning you want the solution of the Poisson equation, this U, to be bounded, then generally speaking, from the intuition you get from in the Euclidean Laplace equation, you want this F to decay at least quadratically bound. So this is, what the general package allows you to do. So in applications, this is a subtle point, because for many natural examples that you can write down, these natural ansatz, you can get the smallness of this error, but you can't get the quadratic, faster than quadratic decay on the nodes. And that's something that you need to work hard for. Right? And what happens with the higher order derivatives is maximum principle similar to what happens in the compact case. Okay, so that's what happens with the analytic package. Now, let me talk about some problems in this field. So one of the fundamental questions is, to what extent is the complete non-compact Calabi Yau metric unique? And what kind of data parameterizes such objects? So the naive expectation, based on analogy with the compact case, is that maybe the complex structure and some Kähler class of cohomological data should determine the metric. Now, this is false, as we already saw in the example of the Taub-NUT metric. Now, Lebrun's observation that Taub-NUT is C2 was historically a surprise, because C2 has, people think, no topology and no deformation. But however, it seems like the historical significance of Lebrun's observation was not that well understood. So for instance, people believe for some time that exotic metrics cannot exist under the maximal volume growth condition. So Lebrun's example is not maximal volume growth. It's r to the cube, not r to the fourth. So there are, in fact, by now we understand there are several ways, several viewpoints from which you can understand Lebrun's example. So people think, Calabi Yau metrics should come from some topological reasons. Turns out that and people think that C2 doesn't have topology, but in fact C2 does have some topology. It's that topology comes from extra data. So for instance, the one on C2 really comes from a holomorphic fibration structure. And alternatively, you can think the topology comes from some S1 fibration structure on C2. And in fact, these viewpoints lead to different generalizations. The first one leads to the main topic of today, which is a complete non-compact maximal volume growth example of Calabi Yau metric. The second viewpoint generalizes to gravitational instantons and high-dimensional variants. So my own motivation for constructing this metric comes from studying collapsing Calabi Yau threefolds with a Lefschetz K3 fibration. So this means you have a Calabi Yau threefold that's complex three-dimensional. People call this Calabi Yau threefold. Holomorphic fibration is basically a generic subversion to CP1. And being Lefschetz means that the only singularities in the fibration are modeled on this quadratic equation. And what one is trying to study is a family of scalar classes with a small parameter t. So what happens is that the fibers are much smaller. So the diameter scale is 4 of t to the 1/2, whereas the base is kind of 0.1. So what happens in the limit is that the whole thing collapses to the base. It drops dimension. The total space is a Calabi Yau threefold. The fibers are K3 surfaces, which are complex two-dimensional. The base is complex one-dimensional, it's CP1. So as t goes to 0, the global Gromov-Hausdorff limit is CP1 with some singular Kähler-Einstein metric, singular metric, so-called twisted Kähler-Einstein or Song-Jian metric. And away from the singular fibers, that is in those kind of regions, what happens is that the Calabi Yau metric is well approximated by something called a semi-flat metric, semi-Ricci flat metric, which means its restriction to the fibers. So in particular, essentially the Calabi Yau metrics on the K3 fibers. So the fibers themselves are also Calabi Yau manifolds for K3 surfaces, and you can talk about the Calabi Yau metrics on those. And turns out if you restrict the global metric to those things, you get almost the K3 metrics. So the motivating question for me was what happens near those singular fibers? So if you try to zoom in those regions, what actually happens? So that was the question that motivated me. And it turns out that this local region sees into an exotic metric on C3. That is the main upshot of this talk. So let me first switch back to the non-compact setting and tell you the main theorem of today. So the main theorem is that there's a non-trivial complete Calabi Yau metric on C3 with maximal volume growth, where maximal volume growth means the volume of geodesic balls is up to the 6th power. So 6 comes from the fact that complex 3-dimension is real 6-dimension. Now, the main feature of this metric is that, first of all, it has this symmetry, SO3, which is clear. And there's an U1, which kind of rotates the base. It kind of rotates the holomorphic volume form, but preserves the metric. Now, near infinity, what happens is that you have a fibration structure. So you have C3 over C. The fiber, so this is the map of Z1 squared plus Z2 squared plus Z3 squared. The vertical direction means the fibers of this thing, means the pre-image of points downstairs. The vertical directions are roughly speaking the Iguchi-Hansen metrics on the fibers. So the fibers are just those affine quadrics which carry those Iguchi-Hansen metrics. And the restriction of this metric of C3 to those fibers is approximately Iguchi-Hansen, that is close to infinity. Now, in the horizontal direction, as opposed to the fiber direction, what happens is that you have a Euclidean metric on C downstairs, and you basically pull back this. So this is an approximate description of the metric, and in particular, the tangent cone at infinity, meaning that you scale down the metric and try to take a limit as the scaling sequence goes to infinity. The tangent cone at infinity is C2 over Z2 times C. So I will show you a picture later, well, this whole setup, where the C comes from really the base direction, and C2 over Z2 comes from the asymptote of the Iguchi-Hansen metric. Because the Iguchi-Hansen metric in the vertical direction is asymptotic to C2 over Z2. So in particular, this metric has maximal volume growth, meaning R to the 6. Okay, so an outline of the construction is that you write down some scalar potential, so near infinity, and okay, so the moral is that you write down some ansatz metric, and then you try to run this Tianyao-Hein package to perturb this into an actual Calabi Yau metric. So that is the moral. Now, there are some subtleties to this, which is that this metric is not quite regular as it stands. So this expression is not even smooth when f is close to 0. So this actually needs to be regularized. And even after regularization, the decay of the volume form is in fact too slow to apply the standard package. So there's an additional step of trying to correct the error. So these are just the technical parts. Nobody really wants to there. Now, let me show you a picture about what this metric looks like. So the metric lives upstairs on C3. The C3 admits a map to C. The fibers are those guys. Okay, these are just defined by quadratic equations. The central fiber is y equal to 0. It's C2 over Z2. Now, if you go to infinity in a fiber, what you see is similar to this. It's basically another copy of C2 over Z2. And so this is what the metric looks like. If you restrict the metric to the fibers, what you get is almost the Iguchi-Hansen metric on the affine quadrant. And the horizontal direction is basically the pullback of the metric from C. So if you look at the analytic expression, this thing is precisely the potential for the Iguchi-Hansen metric. And this thing is basically the metric coming from the base. So that is why I was motivated to write down something like this. It's not literally what happens in the paper, but of course that's what actually happens. Okay, so now there's a small puzzle, which is why do you see C2 over Z2 times C as the tangent cone? So in particular, you can see that there's some kind of topology in the fibration known as the vanishing cycle. So those quadric fibers are diffeomorphic to the cotangent bundle of S2. And those S2s are known as vanishing spheres or vanishing cycles to topologists. So why don't you see this in a tangent cone at infinity? The answer is that, okay, it happens for a metric reason. If you look at the diameter of those vanishing spheres, they grow like the distance to the origin, that is this, to the 1/4. This 1/4, of course, runs on calculation that you don't have to do. But the point is that 1/4 is smaller than 1. So what does this mean? So let me say an analogy. So we observe the starry sky and we see the stars are very, very small, right? But in fact, those stars are huge. So the reason you perceive them as small is because the angular, so the kind of angular length you see is very, very small. So it's really the intrinsic size of these things divided by the distance of those stars to you that affects what you see, right? So from the viewpoint of a very distant observer, well, those vanishing spheres divided by this distance, that's very small. So the fact that this 1/4 is smaller than 1 means so this kind of sublinear growth is what gives rise to this. So independently, Ronan Colon and Rochon and Gabo Zakihidi developed more elaborate linear analysis. So this allows them to obtain exotic Calabi Yau metrics, not just on C3, but in fact on Cn, associated to many other fibrations. So this is only the beginning of a very big general construction. So in my case, I basically did the correction nitty-gritty steps by very ad hoc means. Those people had a much more systematic way of doing this. So later, Gabo proved a geometric uniqueness result for his exotic C3. So that result basically says, if you prescribe the tangent cone to be C2 over Z2 times C, and if the underlying complex manifold is C3, then it's up to scaling, I guess, the same metric as this metric. So it's a geometric uniqueness type result. So that's later work of Gabo. Now, this whole thing has some application to the study of collapsing Calabi Yau metrics in compact settings. That was my original motivation. So as those metrics shrink down, what happens is that if you zoom into a very small neighborhood of the critical points of the fibration, so we are assuming this is a Lefschetz vibration, so locally the vibration looks exactly like the model here. As you kind of zoom in this region, what happens is that you see this metric on C3. So it's worth pointing out that, okay, so this C3 metric has some kind of uniqueness property. So one moral lesson in particular is a kind of universality, meaning you are studying kind of Calabi Yau threefolds with K3 fibrations. Now that's quite complicated in general, it involves lots of additional data. But if you just zoom into what happens around the critical point, that's the most curved region of the manifold. So the local structure of that region is in fact universal. It doesn't depend on the underlying details of the ambient Calabi Yau threefold. It's a universal thing, and the moral reason why this is universal is because this scale is so small. It's much smaller compared to the fibers. So the details about the fiber K3 surface, in fact, was too large. That once you kind of scaled everything, around the curvature scale of this region, then you have pushed what happens, on the fibers. The fibers become almost infinitely large. So the kind of other details of the fiber simply were pushed to infinity. So the theorem is that there's a gluing construction of Calabi Yau metrics using this as a local model. And what this shows in particular is that this C3 arises in the collapsing Calabi Yau threefold problem. So there's another comment, which is algebraic geometrically, there's a way to think about this kind of metric. So algebraic geometry, okay, so here's a general question. So what's the difference between algebraic geometry and complex geometry? So in complex geometry, you have the class of holomorphic functions. In algebraic geometry, you have this algebraic function. Now, what's the difference between these? Now, one answer you can give is the algebraic functions are precisely holomorphic functions with some kind of growth constraint. So, for instance, one way to think about the Cn as an algebraic geometric object is that you have Cn as a complex manifold, plus the fact that you have polynomial growth functions. Now, you can do a similar thing here and worry about on this exotic C3, what are the polynomial growth conditions, polynomial growth polymorphic functions. Now, the answer is that to understand this, you have to understand what the distance function on this manifold looks like. So this distance function is by Herder, at least asymptotically, but not by Lefschetz to the standard metric. The consequence of this is that the polynomial growth functions on this thing is the same class of polynomial growth function as the standard case. However, the filtration induced by the degree of growth is different. So this is the same ring of holomorphic functions, of algebraic functions, but a different filtration. So this perspective is closely tied to Donaldson-Sun theory, and it's in fact reflected in how Gabo proved this uniqueness result. The filtration of functions by the degree of growth is in fact almost like the starting point of Gabo's uniqueness proof. Okay, so let me kind of tie the talk with the beginning of this talk. So how about Lebrun's observation? So remember that Lebrun observed that the Taub-NUT metric is an exotic metric on C2. Now I want to say something about how to understand this as a kind of special instance of this general perspective. Well, where does the Taub-NUT metric come from this understanding? Well, C2 has a holomorphic fibration to C, which is just given by Z1, Z2, or in other words, Z1 squared plus Z2 squared. That's the Lefschetz vibration in dimension 2, right? That's the simplest analog. Now, what's different about C2 and C3 is that if you take this vibration, now what's the fiber of this? The fiber of this is C star. So Z1, Z2 equal to constant. That is a copy of C star. Now, C star is a cylinder, and the natural Calabi Yau metric, it's really too fancy a word to say for C star. The natural metric on C star is the flat Euclidean metric. And that metric has an S1 direction and an R direction, right? So in particular, the way to visualize the metric on this C2 is that you have basically a fibration by cylinders where you have an S1 direction and another R direction. And you have a family of those cylinders over a C, copy of C. Now, in that picture, there are 3 directions of possible growth. So there's a C direction, which gives rise to 2 dimensions of volume growth. Now, along the fibers, there's 1 more. So there are altogether 3 directions of volume growth, but the circles don't grow at infinity. So that's the main difference between the C2 example and the C3 example. In C3 example, the fibers are affine quadrics, and the affine quadrics have degree 4 growth, while for the cylinders, they only have 1 degree of growth. So if you view things from this perspective, it explains why the Taub-NUT metric exists on C2, and it also explains why it doesn't have maximal volume growth. Now, here is the big question for the future, for the young people, I guess. So in general, how would you characterize the moduli space of Calabi Yau metrics on Cn, let's say? So by now, we have plenty of constructions given by people like Gabo and Roland Column and Rochon. But okay, we have some amount of uniqueness result, but certainly not a general classification. So how do you understand Calabi Yau metrics in higher dimensions? Cm would be a very good testing ground for your understanding. So even if you restrict your attention to the class of maximal volume growth examples, that's still quite far from a full classification. That's something to think about. So I guess, am I running out of time? Yeah, okay. Well, okay, so I guess I can thank you for your attention.
Thank you very much for the very great talk. Okay, any questions or comments?
Half volume growth. Okay, so in the case, okay, so for instance, in complex dimension 2, there is by now almost like a classification now of gravitational instantons. So the classification, the rough one, is that there are kind of maximal ones like ALE, so then ALF, and then ALG, ALH. That's almost like a joke, but yes, but there are many ones with kind of degree 2 volume growth coming from essentially elliptic fibrations. So you start with something like an elliptic surface, meaning some compact surface with an elliptic vibration over maybe CP1, and then you remove a divisor at infinity. So those things give you plenty of examples.
What about on C2?
C2, I think that, I think the ones on C2 are just the Taub-NUT and the standard one.
Cannot have.
Yeah, I think these are.
Won't be able to have the on C2 power of the quadratic.
I don't think so. I mean, on C2, I think there are only these two examples. CN, well, okay, so yes, okay, so on CN, you have lots of maximal volume growth examples coming from Gabor. You can, of course, have product type examples, which are cheating. And I have constructed some non-maximal volume growth ones on C3, which closely resemble the gravitational instantons. Those have volume growth 4.
The reason I ask is basically about the, the static Ricci solitons.
Okay, that one you know much more than me. Yeah.
And there's sort of analog.
Yeah. That's okay.
Yeah, maybe this is naive, but you said that by Gabor, so it starts with the filtration.
Yes.
But I guess you would need to know somehow that the filtration was. I guess you cannot start with any such kind of data. You still need some kind of model to actually get the Calabi Yau method.
I think you first know what are the low degree pieces of this filtration. Right. So what you need is that you need to understand the filtered pieces, the low degree ones, up until you can generate everything. And you need to go into the sufficient filtration so that you understand the relation between those generators. That is a rough understanding.
Any other questions or comments? If not, so let's thank the speaker again.